Welcome back to lesson 1.7 of pre-calculus. We've already taken a look at the notes for how to find inverses and state their domain and range. And now we're going to look at the formal test to verify that two functions actually are inverses. While it's true that many of you know how to find an inverse, and that's great, and so you might be tempted, although with rational functions you probably wouldn't be, to try to find its inverse and see if it turned out to be this. There is a formal test that we are supposed to do, and that is that when you're asked to verify that two functions are inverses, the formal test is to show that f of g of x and g of f of x equal x. In other words, when I do f of g of x, fog, and g of f of x, goff, all the operations are done and all I'm left with is the variable x. If I'm left with anything other than that variable, then they are not inverses. And you have to do both. If you do one, that's not enough. It has to be both. That's why the and is bolded there. So let's test these two. They kind of look like they might be inverses, but they kind of look like they might not be given what we know about how to solve for inverses. So let's see if they are. We're going to start with f of g of x. So I'm going to plug g into f. So f is 6 over x minus 4. And into that x, we're plugging in the 6 over x plus 4. When I do this, my numerator stays 6, and the denominator of plus 4 and minus 4, so I'm just left with 6 over x. Well, to divide by a fraction, I have 6 over 1 times x over 6. I'm just left with x. So far, they look like they might be inverses. But wait, there's more. We still have to test g of f of x, because if that doesn't turn out to be x, then they're not inverses. So g of x is 6 over x plus 4. And in this case, we're plugging in 6 over x minus 4 for f of x, or for x. We're taking this and plugging it in for x. The rules of fractions say that I have to do 6 over 1 times the reciprocal of the divisor x minus 4 over 6. We're left with x minus 4. Don't forget to bring down the plus 4. And sure enough, that does equal x. You can't just say it equals x. You need to show how you got there. So you have to do f of g of x and g of f of x and show that they both equal x. So yes, f and g are inverses for this first example. We're going to look at two more examples. In the next one, we have two linear equations. They might possibly be inverses of each other. They might not. Let's take a careful look. So we're going to first test f of g of x. So we have f of x we write down and put in parentheses where x is, and we're going to plug in g of x. When I do this and I distribute, 2/3 times 3/2 is just x. 2/3 times -2 is -4/3, which gives us, this would be in terms of 4/3, 6/3. That's going to give us x plus 2/3, which is not equal to x. So this did not undo the operations to give us x. So I don't even have to test g of f. I know right now that if either one of them doesn't work, then they are not inverses. So f and g are not inverses. Unless I copied down the function wrong, which it does not appear that I did. So we are good there. All right, but if one of them works, that doesn't mean the other one will. We have to check them both. If one of them doesn't work, we can stop the test. In our last example, this one has a quadratic function and a square root function, so we kind of suspect that they might, I think they kind of are, might be inverses. Now they do have, right, we may also want to check the domain and range. This one has for x greater than 0, so that means that this will actually have, if you look at the graph of this function, right, we're only looking at the right half of the graph, so that's fine. And then this one says x is greater than or equal to -2. Well, -2 would have been the range for this, -2 to infinity, that's the domain here, so far that looks good. The domain for, or the range for this, if you look at this function, would be 0, which x is greater than 0. So that's good so far. The restrictions are fine. We just have to be concerned with, does f of g equal x? F of g of x equal x? And does g of f of x equal x? If both of these are true, then these are definitely inverses, and we'll have used the formal test to show that. If they're not both true, then they're not inverses. So let's take a look. In f, we have x squared minus 2, and we are plugging in g, that's the square root of x plus 2. Squaring and square root are inverse operations. We're left with x plus 2, and then we bring down the minus 2, we're left with x. So yay, so far it checks out that they're probably inverses. They look like inverses. All right, let's test it here. G of f of x. We have g, and then for x, we're plugging in f of x. So that's going to give us our x squared minus 2. When I simplify the radicand, x squared minus 2 plus 2 is just x squared. When I take the square root of x squared, I get x. So, because both f of g of x and g of f of x reduced to x, f and g are inverses. You have to provide this work as your evidence of the formal test before you make the statement that they are inverses. Of course, if you have one of them not work, you don't have to test the other one. So that summarizes what you reviewed today from Algebra 2 in class exploration, and it gives you a few more examples to look at. Have a great day.